All right, so welcome everybody to this seminar. My name is Dragomir Kaszlikowski, it doesn't matter. And let me first introduce the speaker, and I will do it my way, so be patient. Well, won't be long, I promise. So first I'll read you a biographical note I have about Marcin. So Marcin Pawłowski obtained his PhD at University of Gdansk in 2010. And shortly afterwards, he was awarded EPSRC scholarship at University of Bristol, where he worked as a postdoc. And soon afterwards, in 2013, he returned to his alma mater to start his own team, which is quite an achievement already. Currently, he is the head of Quantum Cybersecurity and Communications Group at the International Center for Theory of Quantum Technologies. He's also one of the founders of Secure's SPA or SPA, a startup company which builds quantum random number generators. So that's a biographical note, but you know, I don't like such notes because they tell you nothing, completely nothing about the man. And I happen to know the man. I worked with Marcin on one paper, I think, but what a paper it was. And that was because of Marcin, not because of anyone else, not to offend our co-authors and myself. And you know, so who is Marcin as a man? Okay, so let me tell you this: he is fun to be around with and talk physics, especially over beer and coffee, and you know, and after the talks during conferences. And I had the opportunity to do that, and it was always a pleasure because he's so passionate about what he's doing that it seems that for Marcin, nature is like a playground with toys that he picks up and plays with them, and this deeply reflects on his humanity, I would say. And so it's joy to talk science with him. And to end this short introduction, I would say that Marcin, and you will see it today, Marcin is kind of like a crazy professor in the Hollywood blockbuster. But there's one big difference, that Marcin has the essence. So I think that I'm done with my introduction, so please welcome Marcin, and now the floor is yours, and you can correct all the information I provided, like the abbreviations that I didn't know what they mean, but so welcome.
Okay, thank you for the introduction. It was by far the best introduction I've ever had. There's nothing to correct, and thanks again for inviting me to give this colloquium. I'm very happy to talk about quantum random number generators today. And as Dragomir already said, I'm also the head, one of the founders of the company that builds quantum random number generators. So actually, the whole evolution of quantum random number generators, which is the title of my talk, will end with the apex of this field, which is our quantum random number generator. Of course, others who are building them, the different ones, may have a different view on this issue, but they are, without any other introductions, let me share the screen and let's start the presentation. So that's me, and this is the title of the talk, and these are the funding agencies which provided money for this work. So what is randomness? In physics, or more precisely in every field that does work with randomness seriously, it is equivalent to entropy, and the best way in many aspects is to measure it with Shannon entropy, although we use sometimes different measures. But throughout this talk, I will make these two concepts equivalent: randomness and entropy. So what are the uses of it? The most important ones are science, gaming, and cybersecurity. So when it comes to science, we want to have good random choices, because otherwise we will not be able to judge whether the results of our experiments were not biased by the choices of parameters that we made. In gaming, we just want the results of various random choices or lotteries. To be fair, the person here in the photo is Robert Mugabe. He was president of Zimbabwe, and when he was president, he won national lottery in this country. So we don't have proof that something sinister was afoot, but not knowing other things that this guy did, it's highly likely that the random numbers in this lottery were not really random, for him at least. I will repeat this many times in this talk because this is important. Randomness is always dependent on a context. When we say something is random, we should always ask random for whom? Because if I roll a dice now here, I can look at these dice. For all of you, it is random. For me, not anymore, because I see what's there. And the second after I told you the result, it's not also random for you. So whether something is random, it depends basically on your position in space-time. Okay, and cybersecurity. Cybersecurity is the biggest market for randomness. We're using an enormous amount of randomness in our everyday life. Each of you is now using a computer to watch this talk, and your computer needs to generate random numbers all the time just to keep working. Whenever a new process is started by your operating system, a random place in memory is allocated for it. If it were not random, it would open some avenues of hacker attacks. So you really need a lot, and especially if you want to communicate. Everything we are sending now, whether these are Zoom talks or text messages or emails, everything is encrypted. And for encryption, you need random keys. So a lot of randomness is needed. And let me quote Sun Tzu, the author of The Art of War. He was very popular in the American yuppies of the 90s, who basically built their own business strategies based on this book, because they saw what happens in Wall Street just as war, and when it comes to cybersecurity, it's still a war. So knowing the enemy enables you to take the offensive. So your entropy, from your point of view, about the enemy should be as low as possible. Knowing yourself enables you to stand on the defense. So the entropy about myself should be as small as possible, while it is still as large as possible for the enemy. So writing this in information theoretic terms, this is what Sun Tzu meant when he wrote this. Okay, and as I said, randomness in cybersecurity needs to be random for the adversary. It's always the randomness, not for me, but for the adversary, and it's used for memory allocation, passwords, and cryptographic keys. And the first source of randomness were humans. We are really bad at it. So before the enigma was broken in the Second World War, some cases where of communications could already have been cracked because of bad randomness used by some of the people who were sending the messages. For example, the first German military formation whose messages were cracked was Luftwaffe, because they had a tradition to use girls' names as the seeds for the randomness of their messages. And when British learned that, it was very easy to crack those messages. So we are really bad at this. Not even because we tend to get lazy and choose passwords like 1, 2, 3, 4. Even if we try to be random, we're not very bad. We're surprisingly good when we are augmented. So if I take a coin and start to flip it, it will be almost perfectly random, and with very simple randomness extractors, you can make it almost perfectly random. So we're quite good, but we're mostly useless for cyber security purposes, because, as I said, your computer needs a lot of randomness, and we're always slow. So if I did nothing but through coins, I would not be able to provide randomness for a simple laptop as fast as it needs. So, and I have better things to do than throw coins. So people have been thinking of using some automated ways to generate randomness. And in 1946, a great book appeared, 1,000,000 Random Digits. It was published by Rand Corporation, and they used an electrical device which was mimicking the workings of a roulette wheel. And for many purposes, it was great. This was public randomness, so everybody had the same book. But for scientific purposes, since the numbers in the book are random from the point of view of natural phenomena we like to study, this was perfect. Also, we have this concept in cybersecurity, security through obscurity. It means that although it's better to test cryptographic primitives by announcing them and letting as many people as possible to try to hack them, but when we start using some cryptographic protocol, it's better not to tell anyone. So if nobody knows that we are using this book as a source of randomness, it's also good, it's fine. And even now, there are so-called randomness beacons. These are agencies like American NIST, which periodically publish new highly random numbers, which you can use for many purposes, but shouldn't use them for lotteries or cybersecurity, because anyone can anyone will get to know them. The cool thing about random million digits and randomness beacons is that a lot of quantum devices, especially the most advanced ones, they actually need randomness to produce randomness, or they need randomness to produce secret keys. But the randomness they need can be public. So I can take a device which does Bell experiment. Bell experiments are great sort of randomness, but they need good randomness as an input. And what will happen is then the device will basically convert public randomness from this book or a beacon into a perfect private randomness. So these things are not as useless as they might sound. Okay, now, as I said, there are already quantum random number generators, but we also have much better physical random number generators than the roulette wheel that Rand Corporation built, mostly because it was pretty slow. And this is taken from Wikipedia entry on physical random number generators or entropy sources. This is the same thing as I told you at the beginning of this talk. And the question is, what is the difference between quantum and classical ones? I will tell you this in 7 or 8 slides, but right now, I want to tell you what Wikipedia is trying to say, and it's wrong. So keep that in mind. Wikipedia says that if you're using a quantum process to generate numbers, then you have a quantum random number generator. But if you're using a classical process, then it's a classical random number generator. But then what makes a process quantum? I could say that my laptop is a quantum computer because the transistors in its CPU use quantum effects. And if you look at that list, the first on the classical list is, the second on the classical list is a noise generated in a diode. And the first in the quantum is also noise generated in a diode. So is noisy diode quantum or classical? This doesn't make much sense. So I'm going to tell you what makes sense, but in a couple of minutes, bear with me. Now I want to bash at current state of the art devices. So, for example, Samsung has already put on the market first smartphone, which has an inbuilt quantum random number generator. And the random number generator is based on, I think, third on the list here, on the quantum side, photons traveling through semi-transparent mirror. So it's the easiest conceptually random number generator that you can build. You have a laser, a source of single photons, whatever that means, a mirror, which lets exactly half of them get through and half of them gets reflected, and 2 avalanche photodiodes or any kind of photon detectors. Now, the laser is supposed to send a single photon, and if it arrives at one detector, the device produces 0 as a random number, and if it arrives at the second detector, it produces 1. So this is physics. Now engineer comes and notices a very simple thing. So if I always get 0 or 1, then if I'm not getting 0, then I got 1. Then I don't really need 2 detectors. I can have a device like this, and if I find a photon, I say the outcome from the device is 0. If I don't have a photon, the outcome of the device is 1. And these photodiodes, they cost a lot of money. So, so now I made a simpler device, and it's doing the same. But then, now I can look at this device and say, okay, what is this mirror doing here? It's introducing 50% of losses here. But apart from the mirror, losses are also in the medium which takes photons from laser to the APD. In APD, itself, and if this is fiber optical cable in the couplings. So there are a lot of losses. So I can see, and I can also change the amount of losses by playing with different voltage on the APD, parameters of the laser, and the medium. So I really don't need a mirror. I can go without it. And actually, now, this is how a quantum random generator looks like in these Samsung phones. It's just laser or a diode and photon detectors, and whether it clicks or not, it generates 0 or 1. But then I can say, okay, but everybody knows that, well, at least every physicist should know that if you have a photon detector, it has this so-called dark counts. So it says that it registered a photon, and probably it did register a photon, but not one coming from a source. It was some background radiation, or there was no photon at all, and it just clicked. These things happen. So if you, again, play with voltage and the parameters of the environment, you can just go without a laser, and this is what's left from your quantum random number generator. And let me remind you that this is also a classical random number generator, so we really shouldn't call them quantum, because now I give you a better definition. Quantum random number generator is such that it does something that classical random number generators cannot do. And this should be the definition for any quantum technology. So if I have a quantum key distribution, I'm generating a key which you cannot guess, even if you have infinite computing powers. If I have a real quantum computer, then I can do Shor's algorithm, and so on and so forth. So what is that quantum random number generators can do and classical cannot? Okay, I will tell you in a second, but first I forgot that I added these 2 slides saying why classical random number generators are bad. Because this thing that quantum random number generators can do is getting rid of this badness. So a few years ago, a very nice paper appeared. Some scientists took Intel Ivy Bridge CPU, and this CPU has an inbuilt physical random number generator. It's just an electronic circuit which is supposed to produce random numbers. And they did something really cool. They made the smallest modification possible. They changed dopant levels in a couple of transistors of it. So they didn't even change a single part of the circuit. They just changed the electronic properties of a couple of transistors. So you cannot see this change even in a microscope. And they showed that if you do this, the numbers look still random for the user, but are not random from the point of view of the person who knows which of the transistors have changed the dopant levels. And so even if you have if you're building a random number generator, you should trust your manufacturer and also like every subcontractor of the manufacturer. So if you are really paranoid, and this is what's basically the golden standard in cybersecurity, you should check the dopant levels of every transistor that you're using in your device. This is just crazy. So this is a very dangerous attack. Other thing which is wrong with classical random number generators is that even if you buy a device which is certified and looks like it produces good randomness, you should not trust the person who is selling you this thing, because this thing here is the Enigma machine, which I showed a couple of slides earlier. And you should remember that after Second World War, the British made it a secret that they are able to crack it, and all the machines that were captured from Germans, they sold it to their former colonies and could eavesdrop them all the way up to 1970s. So you should not trust the person who is selling you this device. Also, you should not even trust the designer of this device, or the designer of the whole protocol. So there was this big scandal with so-called dual elliptic curve random number generator, which was designed by National Security Agency of the United States. Then they convinced their Institute for Standards and Technology to approve it as a good source of randomness, and then they paid RSA Securities, which are the leading provider of cryptographic devices in the world, to set it as a default. And this was again producing numbers which looked random, but not for them. And finally, quite recently, there was another scandal with Huawei, a provider which put basically backdoor in their routers. So you shouldn't trust the person who is selling you the device. They might be corrupt themselves, or they might have been corrupted by somebody else, or even if they are fair, you don't know if they don't have corrupt suppliers. So, and classically, there's nothing we can do about this. And another thing which can happen to classical random number generator is bad entropy estimation. So how does a randomness generator work? So first, there's an entropy source, which I say it's equivalent to randomness generator, but usually all the randomness we're getting is pretty biased. But this is not a big problem, because with some extra independent randomness, for example, one coming from Randbook or randomness beacon, you can extract good randomness, perfect one, as close to perfect as you want. But there's one trick. You need to have a good estimate about how much randomness is in your source. And this is very tricky, because as soon as your randomness extractor, which is just a classical function, this classical function takes entropy, it takes a string of data from the entropy source, some extra randomness, and a parameter which is the quality of randomness from the entropy source. And this function produces good randomness. And it's good as soon as this parameter is really the correct value of entropy. If it is not, then this randomness extractor is not guaranteed to do anything, and in the worst case scenario, it can actually lower the entropy of the source. And it's very, very difficult to estimate the entropy of any device. So usually people are just taking their educated guesses, but sometimes their educated guesses are not good enough. And this is a figure I have taken from a paper, but I've lost everything apart from the DOI, which is still good. You can find it. Anyway, this is about after pulses. After pulses are an effect which happens in photodetectors if a photodetector detected a photon for some time, here measured in microseconds, it is more likely to detect another photon. Basically, its detection efficiency is a little higher, but also its dark-count rate is higher, and you're taking this into the account. But in some of the experiments, people were underestimating this probability, and it led to a bad estimation of entropy. Also, what happens is that if you have a practical random number generator, let's think of it as a box standing next to your computer for really high security purposes. This is a box size of a printer which sits somewhere in your server room. And now this box is very susceptible to environment. So, for example, there were experiments with NATO-approved military random number generators, which were cooled down and at some temperature, and it wasn't like liquid nitrogen, it's like minus 10 or 20 degrees, they started their entropy really went quickly down. So the entropy of your source really can change during the operation of the device, and even if it doesn't change because of the changes of environment, it can be made to change by an active attack from an adversary. I don't have a slide about this, but there's a very interesting paper in which people focused a beam of electromagnetic radiation on a random number generator, and with this, at a distance, they could reduce its entropy. So you're slowly probably guessing what quantum random number generators can do. Yes, they can estimate their own entropy on the fly. So while they are operating, they can say exactly what their entropy is. And if you put they can estimate the entropy from the point of adversary. So if an adversary before you even start using the devices, put some Trojan horse, they can immediately see it, and if the Trojan horse makes the outcomes totally predictable, they will just say there's no entropy here. And if the Trojan horse works a little, so for example, it lowers the entropy, then they can correctly say what's the real entropy. And if there are no Trojan horses, the device is honest, but something happens to the environment, or it simply malfunctions, or it's attacked, it will immediately see that its entropy is getting lower. And since randomness extractor is just a function from a huge family, and they work for any initial entropy, it can immediately change inbuilt randomness extractor to compensate for the losses of entropy, and it will still, under all same circumstances, produce perfect randomness simply at a slightly lower pace. So the best, well, in some sense, but one of the coolest quantum random number generators are Bell tests. So if we have a pair of entangled particles and they are measured at two different locations, we have this expression known as a CHSH inequality, and it can be shown that if you just look at the value of this expression, don't assume anything about what's happening in this brownish orange boxes, this is how much of entropy you're getting. This time it's mean entropy. It's a different measure than Shannon's, but for all intents and purposes, it does not matter much. If you look at the plot here, you will see the blue curve, which is actually a straight line, and this is really cool. So even if you don't believe in quantum mechanics, but only assume that the universe should be no signaling, you still get some randomness. And this, as I said, doesn't depend on anything. So if somebody played with your source of entanglement states that it doesn't produce perfectly entangled states, or some devices are a little crooked or something, as soon as it doesn't affect this CHSH expectation value, which is beta here, it has no influence on randomness from the point of view of adversary. And if it influences this CHSH expectation value, then you're immediately told that your randomness is a little worse, but fear nothing, as long as it's above 2, which is the quantum classical bound, you can still extract as good randomness as possible. But there's a problem with Bell tests. You need to do a real Bell test, loophole free. So this is extremely difficult. You need really powerful fridges, which take a lot of power, space, and money. And if I want to have a cell phone, I'm not going to carry like a small building full of equipment behind me in a trolley just to provide randomness for it. And also it costs a lot of money to do a loophole-free Bell test, and it's quite slow. So we need something better. And my first idea was something called semi-device independence. So let's make black boxes. So we don't want to assume anything about the devices, like in the test, with a small exception. And this exception should be as small as possible. And our first idea was to say, okay, we have a source of states and a measuring device, and we don't assume anything about their inner workings apart from the Hilbert space dimension of the system being sent from Alice to Bob. And this was quite a good idea because, okay, so if you have a random as a generator, you don't trust it, you want to certify it. You're a certifying agency. You can either test every single component and look for everything, or you can just look if the Alice's device is really has access to only this degrees of freedom and then bound the Hilbert space dimension, and also the same for Bob's device. Even if Alice encodes more information and therefore the Hilbert space dimension of the system is much higher, if Bob's device doesn't have access to it, it's still good for semi-device independence. But the problem was that it's not so nice. It's really difficult to check it. So we were not happy with it. And some people had different ideas, but all of them require you to put a trust in something, whether it's the energy the system is using, or some unambiguous state discrimination. The good thing is that companies are taking notice of it, and several companies are working on quantum random number generators, which are really quantum. So devices which can estimate their own entropy, but they always estimate it based on some additional assumptions. The only exception is, I think, Cambridge Quantum Computing, which wrote a paper and probably filed a patent application for a device based on Bell test, but it's actually nothing else than IBM quantum computer. So basically, you need to have a quantum computer to do this. Others are working on these different versions of semi-device independent. And I don't like the semi-device independent, although I think it was me who came up with the name. So let me, and I already told you why, but I think there is a third scenario, and this is what the whole talk was getting to. So let's recap. In the semi-device independent, we have 3 black boxes, which in reality, these 3 black boxes here do not correspond to different parts of the devices. Inputs can be somehow inbuilt in the source, or you might have actually more boxes, but let's just stay with it like this as a basic
Marcin,
yes?
sorry to interrupt you, but on my screen I can't see your slides, so I wonder whether everybody has a problem or it's my problem only.
Okay, maybe
yes, somebody said there is a problem. Yeah, sorry to interrupt.
Okay, how long?
Now it's before it was bearable, but now I really don't see the almost nothing.
Okay, I'm stopping sharing, and I will share my screen again.
Okay, thanks.
Let's see. Do you see it now?
No, still is shifted to the left on my screen. That one is okay, but the next one is not. Oh yeah, I can't see anything almost. Yeah.
Ah, okay.
Maybe I suggest, Marcin, just display maybe your not the full screen, but just yeah, like this.
Okay.
Now I can see everything.
Now?
Yes.
Okay,
yes.
Okay.
Thank you.
So let's stay like this. That's a little unfortunate, but okay. We have these three scenarios. Semi-device independence has a schematic like this, while device independent, based on Bell inequality, looks like that. And the most important thing, which is why why Bell tests do not require any additional assumptions, is that inputs, that there is no arrow going from one of part of the inputs to both detections. So somehow each detector station has only access to part of the input, and if somebody put some malicious programming in the detection station, and this is like the simplest way to attack any random number generator, then this detection station is oblivious to the full input of the whole system, and simply cannot pretend to produce good randomness and pass the test. In this case, violates HSH inequality. But now I have another idea, and this is something I call Delphi. In the next slide, I will explain what I mean. So it looks very similar to device independent scenario, but when the messages from inputs to detection stations pass through some interference region. If you think about this more closely, it looks really like Mach-Zehnder interferometer, and this is basically what it is. Now, the thing is that if I don't trust this interference region, if it was really a black box, it could just take the message from whatever comes from the source, take all the inputs, make some calculation, and then there would be no difference between Delphi and semi-device independence. And this is why the interference region is gray. I'm not trusting this completely, but I'm putting a very, very limited amount of trust in it. So here's the next slide, and Delphi stands for dishonest electronics. So I don't believe in the detection stations at all, and physics are honest but imperfect. And the only honesty is that I'm trusting that this element here is only about interference. So in practice, somebody can open my device and look at the beam splitter there, and they will not be able to say if it's 50-50 or polarizing or whatever. But what I want my users to trust is that this interference region doesn't have inbuilt detectors, sources, and microcomputers. And this is very, very easy to check. So, and as you see in the previous slide, it looks really like device independent, apart from this interference region, which is very easy to trust. It looks really like a Bell test, so it's really easy to show, and I can easily do it, that it has all properties of device independent scenarios. So I now call it Delphi, but it's a bad acronym. So I have an open contest. If you can come up with a better acronym which reflects better what I want to convey here, I'll buy you a round of beer. So, and what I want to convey here is that the only thing we need to check if this small gray object is really only creating interference. And now the idea, with this idea, I went to some experimentalists and they like it so much that we set up a company. The company is called Secure. SPA, the company is set up in Chile because this is where we got our investors, and SPA is just basically some sort of acronym you add to a company if it's very simple company in Chile. So the company is called Secure, and our device right now is a prototype, and it just lies on an optical table, but we have an industrial designer, and this is how he says the device will look soon in a couple of months. And this is how much entropy it's now generating. And the assumption here is that that our detectors are non-photon numbers resolving. And this is something that I wanted to be completely honest and put right in the open. So when I'm saying that this gray object should be only about interference, I mean it should be only about interference in every degree of freedom that matters. And if my source was able to send a lot of photons in a pulse, then even if the interference region is doing only interference, my detectors could be, and if my detectors are really developed by malicious person and they can resolve photon numbers, you see, this is a lot of ifs, but then this malicious person could attack this device. So assuming that the detectors are non-photon numbers resolving, it's not a really bad thing. And actually, we can get rid of this assumption and say and have a different curve based on how much information about photon numbers the detectors can get, and for every finite amount of information, we get a curve which gives us some entropy. And since we can get more than 10 million runs per second, we're getting megahertz rates of randomness here, which is for randomness of that security level, really nice achievement. And because I'm running out of time, I'm very happy that I have only one final slide to show you. It tells you how I'm estimating randomness. So as I told you, this device is basically Mach-Zehnder interferometer. And if you remember it from your basic courses in quantum optics or even classical optics, if you choose your inputs, or which are basically phase shifts in a correct way, you can have all the photons in one detector, like on the left-hand side, all the photons in the second detector, like in the middle, or 50-50 split. And this is exactly what this device is using. If I get 2 zeros, I should see all the photons here. If I get 2 ones, I should see all the photons in the other detector. And if I have inputs 0, 1 or 1, 0, I'm expecting a click with 50% chance in either of the detectors. And the cool thing is that if, and remember, for the device to be dishonest, both detectors should know all about the inputs. And if these phase shifters try to convey something about its input to both detector stations, what they are effectively doing, they are changing the state of the photon, of the signal, and making it, in principle, distinguishable from the other photon in the other arm of the interferometer, which ruins interference. And that's all. By looking at how often I'm observing a photon in the left-hand side case or in the middle case, in a detector where in which shouldn't observe a photon, I know how good interference is, and I know how much information about all the inputs leads to the detector station, and I can estimate entropy and have a really good quantum random number generator, which can estimate its own entropy and be secure against all the attacks that I've mentioned. And I think I ran out of my time, so thanks for your patience, and that's all. Thank you.
Okay, thank you very much for your talk. As usual, it was a pleasure to listen to you. So now I guess we have time for questions. So there are two options. Either you can type the question in the chat if you for some reason don't want to reveal your face or your identity, or you can just ask the question like me, just by unmuting yourself. And actually, can you unmute yourself, guys? Or I'm not sure, but if not, you can ask me or one of the.
I think you can. Everybody can unmute yourself.
Yeah,
but
yes.
I already have one question in the chat, and it's from Jang Hee, whose face I know, so I don't know why it's in the chat. And he asks, does the interference part consist of something of something like beam splitter? Exactly. And it's exactly in order to raise the information when the inputs are coming. So you're right. It could be a beam splitter. In our case, it's since we're using fiber optical cables, it's basically two fiber optical cores coming close to each other to allow for photons to go from one to the other. But basically, it's a beam splitter.
Hello. Can you hear me?
Yes.
Hi. Hi. My name is Leonid. I'm from A-Star. Thank you for your talk. Very interesting. Very nice slides. Also easy to understand. Very good design. Thank you. So I have a practical question about this interference experiment. So one concern that experimentalists might have is the sensitivity to phase drifts. So unlike to the scheme with, say, a photodiode and laser, or anything based on the dark noise, that's like from a practical standpoint a very stable system. So here you have to deal with the alignment of the arms of this interferometer. So how does that affect your result? Thank you.
It affects it a lot, and thanks for this question. And also thanks for noticing that my talk was clear. To make my talk clear, it was about Mach-Zehnder interferometer. The interferometer which we have in the prototype is actually a Sagnac source, and this makes pictures much less clear. So I used Marcin in the pictures, but all the results are the same. So we're simply not using Marcin, we're using Saniac.
So the phase drifts in Saniac doesn't affect your result, is that?
Yes. So actually, I'm a theorist. When we started this company, like one of the first things my friend said, like we cannot use Marcin, we will use Saniac, and we spent a lot of time proving that all our results carry to Saniac. And this is what they told me, that the reason why we use Saniac is phase drifts, and they are not issue here. I really have to trust them.
Thank you.
Okay, any other questions? Please just feel free to ask. I have a question maybe then. So it's very interesting that you establish a company. I would never suspect you of that, but it's a good move. I think that's the time to transition from theory to practical things, to actually keep the field going, in my opinion. And so have you sold any of those random number generators, or you are still in the process of?
They are not built yet. We have a prototype, but and also what we have is a prototype for a device which will be the size of a printer. Basically, it will fit in those rack cases, and we have an investor which says that when it is ready, it will buy some from us, but we don't know how many of them. But still, since we have funds for the development, we're developing it. But at the same time, we want to build integrated optical chip versions of it. So instead of being size of a printer, it will be size of a small coin. And for they will actually have Marcenders on board, and this is still under development. So as soon as they are built, we're hoping to sell them. But with these deep tech companies, it's really you shouldn't expect to sell anything quicker than 5 years after establishing a company, and we're only 3 years after that. So yeah, but if you want to buy pre-order one, I will be happy to sell you some.
I mean, I have good sources of randomness in my family, so so for my practical purposes, it's just enough. But there's another question: how small can your QRNG be, like chip size?
So I already started to answer this question, and well, there are no lower limits. The lowest limit is actually the size of the photodetectors, but also the size of the interference region. And this is quite tricky because, as I said, our assumption is that the user, or maybe not even the end user, but the certifying agency, which puts a stamp that it's a good thing, should be able to check it. So they should be able to check it under a standard microscope. So the smallest should still have a couple of millimeters, but then there are some also other problems. If you're having an optoelectronic chip, you have to etch the waveguides into a chip, and based on the material from which the chip is built, there are some limits to curvature of the paths. So right now we are thinking about an experiment with etching in glass, and then our chip will not be that small. It might have a centimeter or two. So it's a very complicated question, but I think we can get to maybe a centimeter square, something like that.
Andrew, please go ahead. There's some next question.
Hey, can you hear me okay?
Yes.
Yes.
Okay, cool. Yeah, sorry. So my device is the opposite. My camera doesn't work, but my mic does. Yeah. So my question is more about I guess quantum random number generator in general. Earlier in your talk, you've been mentioning that you can like measure the randomness by using the entropy. I'm just wondering. So I read this paper some time ago that kind of like generate or kind of like test randomness using Kolmogorov complexity instead. And I'm not sure if you're familiar with that, but I'm just wondering, in general, are people looking into that?
Well,
quantum random number generators.
So the thing is that quantum random number generators are like my favorite of quantum technologies because this is something we can really build and sell on the market, and you don't have to be Google or IBM to build a quantum computer. So it's really something very practical. And since everybody is measuring entropy in practice as mean entropy or Shannon entropy, so this is our figure of merit. If I come to a company and I want to sell them, I am not going to use some different measures of complexity. And correct me if I'm wrong, but I don't think you can put a lower bound on Kolmogorov complexity. And this is a big problem because what I want to be able to say about my device is I want to put a lower bound on some measure of randomness. And for Kolmogorov complexity, you'll never know if somebody isn't smarter enough to find even lower bounds. That's a problem. So this is why we're not using it.
All right, cool. Thanks.
Christian, then you are next, please.
I hope it does. So
I cannot hear you.
Can you hear me now?
Very badly, but I'll try.
Does it work now?
Yes.
Okay. Sorry for that. So have you tested this outcome of this random number generator with typical standard tests? I mean, of course, you cannot never test whether it's really random or you can just measure entropy somehow, but have you run some of these die-harder tests across your system?
Almost. So we should have done it by now. The device is ready, but Chile was in lockdown and they locked our access to the lab. So we're hoping to run these die-hard tests maybe next week, maybe in 2 weeks. Soon we will get the answers, but right now we only tested it for very small samples, like 1 megabyte, which is not enough for these tests.
Okay.
Yeah, pandemic affects everyone.
Okay. Well, thanks.
Okay, Marcin, there's another one in the chat. You can have a look.
Yes. So yes, there is, but then the question, so you, as I said, need to have a randomness extractor, which is basically a function which takes bad randomness and its estimation into good randomness. And our device should have this. But then there are two options. You can either provide bad randomness and estimator, and then take the user's software deal with that, or you can put this into FPGA, so basically in the electronic circuit of the random number generator. And our prototype doesn't have it, so it's done by software, but we want to build two versions of our device, one cheaper with users' software taking care of it, and the other a little more expensive with this device doing this on its own, because this randomness extraction it requires quite a lot of computing power. So it's nothing for a laptop, but for an FPGA chip, it might be something. So we need to buy more expensive FPGA chips and so on. So we haven't even decided yet which will be our flagship product, with the better FPGA or with the worst. So I hope this answers your question.
Okay. Any other questions? I have a silly question, okay, that you can laugh at this if you want. So I think that some time ago there was this limitation in some countries on how many bits of cryptographic key you can have, right? I think like 128 bit or something like this. So there's some limits. Do you think that governments will be controlling this kind of stuff on how many bits of randomness you can generate, or it is?
I think they will try, but in most of the countries, I think that especially after the Snowden leaked the particulars of how NSA was trying to force everybody to use bad randomness, they will have a lot of resistance from corporate and private sector. So I don't think it will happen, especially now that we found that in Europe, people have been eavesdropped by the US, which should be our friends on paper. So I don't think they can manage to do this.
Maybe soon you'll be involved in some spy business and you'll have KGB spooks on your door. That would be fun.
So it's quite likely that I already am. So I talked to some people, and it looks like everybody who wrote more than a couple of papers on quantum crypto has already a file and a cool nickname. I hope I have I think you and Christian, you also have dossiers in more than one agency.
Okay, we will deal with that somehow. Okay, it's 15 past 5. So any last question? If anyone has a question, then to be last one. I mean, you can have more, but I'm just trying to pitch this up. Okay, I don't see anyone, at least. All right, okay. So Marcin, thanks for this, and thank you for being, ready for on such a short notice, because it was really crazy, and I knew you would agree because you are like this, so that's great.
Thanks for inviting me. I only wanted to say that I have given a similar talk already 2 or 3 times, but every time I modified to make it better. But I think it was because of your introduction, everything went really smooth, and I think I gave the best performance ever in this. And also, I think I have the best questions ever. So thanks for inviting me here, and thanks for all the questions. It was really a pleasure.
Great. It was our pleasure to have you here.